Thank you. Thanks, everyone. Thanks for the opportunity to speak here. And Leila, you pronounced the name very well. So, Josef Kamleitner is my name. And I work at Siemens Advanced Solutions. And I'm in a team of data scientists and developers where we develop solutions mainly for grid operators in Austria, but also all over Europe and in the US. And one of our focus is predictive maintenance, where I will present the cable use case today, but we are also looking into circuit breakers, transformers, where we then apply different models. So we are generally looking into assets. The results of today were mainly from a project we did in a co-creation proof of concept with the operator in the southern part of Austria. And we also had then a project in Germany, and now we're starting one in the US. Yeah, so the solution is getting bigger and more stable also, yeah. Yeah, why do we do cable analytics? Yeah, basically it's one of the reasons is to prevent failures. And why do we get failures? It can be one of the most important failures is that there is a construction work and it's just by a human or a machine controlled by a human destroys the cable. And that's actually a separate topic, how to predict that. So I will not really cover that because that doesn't really depend on the condition of the cable itself. Yeah, it's an external event that is yeah, not so easy to predict. So you can do it with satellite images and so on. What we rather look at is cable overloads. In particular, when they're regular, they can increase the aging of the cable. When there is a moisture in the insulation material, so it depends on the surrounding of the cable. When there are repair activities of the DSO themselves, or any weather or environmental influences, but they are usually less important than for the overhead lines. And this can yeah, lead to high costs. So one of the needs of the grid operator is to reduce the risk of a cable failure, because then they have outages. Another thing is also they want to manage their assets more efficiently, so to save money, so that they yeah, don't need to dig during the night when there is the outage, but they already do it maybe beforehand, or when there is another a gas pipe put there next to it, and they exchange the cable. Also to optimize investments, so to maybe keep cables that are still in a good shape longer in operation. And then in particular now for the new project in the US, there the safety is a very high concern, because they have a different kind of grid where they have these manholes, and then the people are getting down there, working there, or they can blow up even. So there it's also the safety issue. Then the model needs to have a different target. So that's what we will do in the next months. Yeah, what was done in the very past? This is the classical asset management typical approach. So you see on the left-hand side the new cables. So to the right you have the asset age, and yeah, what you can do when you have a power grid, you say, okay, all cables that are older than 50 years, they are bad. I replace them, and so I have a cycle of 50 years, and I will never have an older cable. So all the cables will be new and will survive. Of course, that's quite expensive, because you will replace many cables that are still in a good shape. You have a high risk, because you might have cables that are 30 years old or 20 years that are already in a bad shape, and you will not have replaced them before they fail. And it's also very inflexible, because typically in the past the grid operators had some initiatives to replace overhead lines by cables. We are mainly talking here about medium voltage cables, 10, 20 kV grid. And now when you're just looking at the age, then you would have now to reproduce the same wave, but with the current budget restrictions from the regulators, this is typically not possible. What we also often see is that utilities want to get rid of one type of cable of this, because there are different generations available. Good. So the next thing that they do now typically is they do some measurements. So then they get an idea now in the Y direction, what is the condition of the asset. You can take the cable off the grid, do a measurement, and you can have one truck with this equipment to measure 200 cables a year. So you will get quite nice picture, but you will still have many question marks because you cannot measure all the cables. You can maybe measure 5% of the cables per year. Otherwise, yeah, just if you have lots of money, you can measure everything, but no one does. So you will, yeah, if you have a good targeted diagnostics, you will be better than the previous approach, but still you have a high risk on the blind spots where you do not have information. So if we have, yeah, some information on some of the cables, we can then of course apply machine learning to predict the state of the other cables. So now we have a asset risk that is modeled, and we can leverage the internal external data and also look at the influential parameters, and that way we can have an optimized investment planning, so we can keep the low risk assets long in the grid, and we have also then for the diagnostics and maintenance activities, we can focus them where the cables are in a bad condition, or for the diagnostics we can focus diagnostics where the model has not such a good performance. Yeah? So maybe some of the cables have not been diagnosed in the past of a certain type or location. So we have now up-to-date risk value for all of the cables, and the bad cables are then most of them replaced before they fail. So how did we implement that? So one big step was the data preprocessing, which was most of the work. More interesting here at the AMLD is the survival analysis that we applied. So a question, who was in the survival analysis workshop on Sunday? Oh, it was on Saturday, I think. Okay, a few. Yeah, so I think you could reproduce the results that we have obtained. So it's not more magic than what we had in the workshop. The data processing, that's also not magic, but it's quite a lot of work, because we have, I mean, here, this is the data wish list. We have asset data, where it is located, what type of cable is it. We have past outages, and there it's important to have a long history of outages. In our case, we had about, I think, 400 outages in the history over 30 years. So then you can kind of get have enough training data. Yeah? If you have a too small grid, you might have issues. You need to have maybe some, take a model from another grid and transfer to transfer learning or so. Then also repair and replacement activity, so always update the asset status. And that's basically what you need as a basic data set. And then it actually in industry, it depends what else you can get with a reasonable effort. Yeah. So for instance, diagnostics measurements, that's typically no problem if they have diagnostics and they can easily map it, we can map it to the cables. Operational logbook, so what was the past load on which cable section, that's sometimes quite difficult to obtain, more difficult than you may think. And then there is also sensors. So typically we try to get as far without putting new sensors there, because then we can start right away. The model will not be perfect, the prediction accuracy, but we now in the US project, we see that the sensors, they have already sensors in the grid, but now the sensors will be at the end of life soon. So that's also a problem if you're looking at transformers, at cables. These assets, they stay there for 50 years, for 70 years maybe. And I don't know a sensor that, IoT device that lives that long, just the communication way, so like 3G is being turned off in some countries. So that's also a problem. And then external impacts like flooding and so on. Good. So for the GIS data aggregation, we put a corridor along the cable. Then we integrate over open source data. There in Europe and in Austria, we are quite lucky to have lots of open data available, like is it a city there, is it a forest, is there a flooding area, was there a landslide, or an earthquake, and so on, so natural disasters. So then when we had the data aggregated, we wanted to use the survival analysis. So you can see here the event timeline. So the check mark in green is always when the cable was put in operation. This can be 30 years ago, 50 years ago. Then you have the blue line. This is the life of the cable where it's in normal operation. And then the first line you see, we arrive at today, and the cable is still in operation, and we don't know what happens in the future. So this is, in survival analysis, a sensor data. So you don't, you know the history until now, but you don't know how it goes on, if it fails tomorrow or if it fails in 20 years. Then we have kind of data with faults in the past, which is the second one, where it was put in operation maybe 50 years ago, it failed 20 years ago. Then the third one is similar type. What's also possible is then that, and these are only few cables where you have a fault, then this part of the cable is replaced and then it's put into operation again. And then it might still live, or it might have several faults and so on. So there are different situations, and to address all these situations, you actually can apply a survival analysis model, which takes in particular into account this censoring at the end of the observation time. If you were in the censoring, in the survival analysis workshop, you might also know there might be also left censoring. This would be the case if you would not have data from maybe earlier than the 70s, then you would not know when the cable was put there. Luckily, in our first two projects, it was always the case, but it's always something we need to check, and we might also account for that. So then here, I cannot show you the exact distribution, just some anonymized few examples. So you can see on the x-axis you have the duration in years, which is here I've zoomed to 50 years, and the survival probability. So you can see that over time this goes down, and the one cable that is as here the bottom line, it's around 20 years. The probability that it fails is about 50%, and then it goes down to 20% that it survives the 50 years. So for 80% it will have failed within the next 50 years, and others tend to live longer. We compared different approaches for survival analysis. First, we looked at the accelerated failure time model to fit that to our data. We did that choice because we did all the data integration in Spark, and Spark provides an accelerated failure time model. So we said, let's try that one. It's the easiest. It did not perform that well, so then we looked into the Cox proportional hazard model, which is also available in Python packages. That was quite good, and so we kept that. We also had then in our project team someone who is very good in R, so he also looked into a stratified counting process model to account better for these reoccurring events. So then it's not only predicting the events, but when you have on one asset you have more events over time, then you can model this as a counting process. This was also quite good, but with the Cox proportional hazard model we had a similar similar results. And we also looked into stratified versions, which means for different categories you do a separate survival line, and there we saw that one of the materials, the PE cables, which were mainly used in the 70s to the 80s, mid of 80s, I think, they have a worse performance than the newer cable types. And that can also be seen already like just empirical, that some of the grid operators are trying to replace all the PE cables in their grid, even without machine learning. Yeah. But there also our model can help to determine which of the PE cables you should put out of operation first and replace with new cables. Yeah, so the model results were basically concordance index was not super close to 1, but a bit above 0.75. And the main influential parameters were the number of past events, the number of cable sections, a fraction of urban area. We did not take directly into account the construction works, but in the urban areas, you typically, even when there is no outage due to construction work, it might be damaged. There are reparations from the traffic on the streets. and there is also typically higher load. Then the cable material was very important, and we translate this to the results in the field that we saw then in the year after deploying the solution, that 80% of the outages were within really the top 200 cables that were at highest risk, and 90% were in the top 400. So if you restart then replacing these cables, renewing the grid there, you can get a significant reduction of the outages. And also for the investment protection, there we saw a bunch of cables which have really low risk, although they are already very old. And so they will keep them in operation for 10 years or more, even though they would have planned to replace them. Okay, so I think I'm running out of time. Yeah, basically we have built an application, a web application that gives the user all the insight in the model results so they can use it in their planning department. So we have no automated decision making. There are several parties in the grid operator involved, and they can use this web application to dig into the details and then make use of it for the decision, because often it's like has to be aligned with the water grid when there is some digging in the cities in particular, and also with the long-term planning of the grid development when the load is going up. That's just a figure that our solution now is being extended with some cable diagnostics and inspection. So we not only prioritize the planning for the maintenance, but also then to gather the new data with the diagnostics, with online and offline sensors, how to improve the model best with new measurements. So these are the key results, that we can analyze the cables quite well, reducing the outages, shifting investments to save costs, increasing the lifetime, and also optimize the diagnostics efforts. Okay, so thank you for your attention, and I'm now here to answer questions.
So questions? We have time for just one, I think, and you win.
Thank you. So I just wanted to ask a question. Maybe I missed this, but as I mentioned before, I work with island Bornholm, and it's connected by a cable to Sweden, which is constantly cut off by the ships. So I am just curious, in your simulations, do you treat differently cables that are at high risk because of the high, let's say, current level, or that are overloaded, like constantly or more frequently than others? And also on those that are, let's say, in danger because of the outside conditions?
Yes, in principle. So from the outside conditions, like environment and so on, we had the chance already in the first project to integrate that. Unfortunately, so we also wanted to integrate the load, the overloading, but it was just too difficult in the scope of the project. It would be have too much effort to integrate the data because it's on different IDs and so on. So we didn't do that, but for the next project we have done that, and also for the future one we are envisioning it. Then it also gives you a really much better picture, but already without the load data it was a good result. Yeah.
Thank you.
There it was maybe the proxy that inside the city it's more dangerous because there is typically more load on the cables. Yeah, so maybe the model caught it via this proxy.